Number one, which is the multiple choice. They're telling us that various options are provided as possible answers to the following questions. We need to choose an answer, only the letter next to the question. The question number one, a box is shown resting on the ground, okay. Newton's third law implies that 4 forces of equal magnitude are involved. These forces are labeled P, Q, R, and S. Okay. And they are telling us that forces P and Q are acting on the box. Okay. Forces R and S act on the earth. Okay, and then for clarity, the forces are shown slightly separated. Okay, we can see that. Then which statement about the forces is correct? So they're telling us that forces P or force P is equal but opposite to force Q, and both are forces of contact. Force Q is equal but opposite to force P, and both are gravitational. Okay. Force R is equal and opposite to force S, and both are forces of contact. Okay. And let's see. Force S is equal and opposite to force Q, and both are gravitational. Okay, guys, so from this question, when we talk of contact forces, I'm gonna remove this out of context, especially if I'm looking at P and Q, if I'm looking at R and S. I'll go for D as my correct option. Okay. Then 1.2, they're telling us that there's a child that slides down a hill with an acceleration of A, and the hill makes the angle of inclination theta with the horizontal. What is the total mass of the child? And its age is M. So the total mass of the child, and whatever this child is seated in, is M. And then the acceleration of free fall is G. The frictional force is represented by, okay. So guys, what do you think? Because we know from our F net is equal to MA. Then when we look at this boy, since it's going down, which means the frictional force is up, and downwards we shall have the FG parallel will be acting down. So which means if I get my frictional force minus my FG parallel, it must get MA. When I move the FG parallel that side, is going to be MA plus FG parallel. But we know that FG parallel is the same as MG, the sine of theta. So I'm seeing M is common, take it out, I have A plus G sine of theta. So I'll go for option. Is it gonna make sense for me to say option D? According to my calculations, that's what I'm having. Okay. Whoa. Just a moment. Something is not adding up here. Since the boy is sliding down, which means the FG parallel must be bigger. Okay. But is that going to change a thing? It will change quite a lot. Let's see. Okay, so I'm going to move this that side, I'll move this side so that our F is the FG parallel minus the MA. So this is mg sine of theta minus ma, take out the m. Then we have the g sine of theta minus a. Yeah, that is a lot. So option C. Then 1.3, they're telling us that a small snowball falls freely under gravity after being released from rest. Which graph best describes the variation of the height, okay, of the ball with time when using the ground as the reference? Okay, now if the ground is being used as a reference, which means the distance between the ground and the graph should get smaller, okay? And since we're talking about the variation of height, which means it's a position time graph, so we cannot have straight lines under the position time graph, okay? And then in this case, okay, part B, I think this makes sense, that the height will decrease as the time increases. Okay, we cannot use C because there's no way the height will rapidly reduce as the time increases. Then this, the reference point is not the ground, it's basically the point of release. So B is the best option for 1.3. Then 1.4, they're telling us that if air resistance is negligible, what's the total mechanical energy of a free-falling body? If air resistance is negligible, the total mechanical energy of a free-falling body increases, decreases, becomes zero, or remains constant. So remember, we're talking about mechanical energy, which is a combination of the EP and then the EK. We know that at maximum height, the EP is going to be maximum. Okay, and then at minimum height, the EK is going to be maximum. But from the conservation of energy, there will be no addition, there will be no increase or decrease. It must be the same. So option D would make a lot of sense. Then 1.5, they are telling us that the diagram below shows two identical spheres, X and Y. Okay, initially X moves with a velocity V, or with a speed of V, directly towards Y. And then Y is stationary. So this one has an initial velocity of 0. This is a V. But this one is moving. The spheres collide elastically. The following occur. Okay, they are telling us A stops, or X stops, and then Y moves with a velocity of V. Okay, let's move on and see. X moves with a velocity of V to the left, whereas the other one remains stationary. Okay, see, X moves with a speed of a half V to the left, and then moves with a speed of a half V to the right. And then D, X moves with the speed of a half V to the right, moves with the speed of half V to the right. Okay, so we know that when we talk about elastic collision, remember there has to be conservation of both momentum as well as kinetic energy, okay? So if I look at the total kinetic energy before collision, it's just gonna be a half mv squared. There is no kinetic energy here. So this must be conserved even after the collision, okay? So if I look at the last statement, a half v and a half v, it's not gonna give me my a half mv squared. Why? Because it will be a half times m, but then my v is a half squared now, okay, or a half v squared. When I square that, I'm going to get a quarter times a half, I'll get 1 over 8 mv squared. When I do that to this, which is also 1 over 8, which makes no sense, okay? Same story with this will just cancel out to be a 0. Then moves with a speed of v to the left, and this one remains stationary. This would make some bit of sense. But now, if the direction changes, then that becomes a problem. Okay, let's see. X stops, which means the velocity is going to be 0. And then this one moves to the velocity of v. This is the most true statement, if there's a word like that. It's the best I can see. Then 1.6, the direction of an object's momentum is always the same as the direction of the object's what. Okay. If momentum is moving to the right, what else is going to move to the right? Is it the velocity? Is it the weight? Is it inertia? Is it potential? So in other words, when you talk of momentum, which quantity, physical quantity goes with momentum? And it's basically velocity. Okay. Then 1.7, they're telling us the satellite orbits Earth at a point X. The gravitational force on X is a quarter of the gravitational force it experiences on the surface of the Earth. Okay. Now they're telling us that if the radius is r, and then the height of the satellite above the surface is going to be how much? If the radius of the Earth is r, what's going to be the height? Okay, so that height is going to be like the distance in between. So whatever distance you get, remember gravitational force is this and that and that and that. We need to attach r to that. So remember from our f, we have g m1 m2 over r squared. Okay, but they told us that at this point, the gravitational force on X is a quarter the gravitational force it experiences on the surface. Does it make sense? Does it make sense? Okay, so if this is the force that it experiences just at the surface, which means this is going to be r squared. Okay. Then, if this is going to be a quarter of f is equal to g m1 m2 over this distance that I don't know. I can call it maybe p, but squared. But I know that this f of mine is the whole of that. So a quarter g m1 m2 over r squared is equal to g m1 m2 over my p squared. So this is going to cancel that. I'm only left with 1 over 4 r squared is equal to 1 over p squared. Can do the cross multiplication. So p squared is equal to 4r squared. Remember, my interest is to get p and take square root. Okay, p getting twice r. Does it make sense though? Does it make sense? Does it make sense? Does it make sense? Just a moment, there's something I'm seeing that I might have omitted. This is a p squared. Yeah, it's fine. But I know that if the distance between the centers, if all of this is my p, okay, so which means there is r hidden within the p. Okay, if this is a y, I don't know why even call it p, but so it's going to be a y plus r is equal to r. and I'll take the R that side, which means my Y alone is going to be, since the question is asking the height of the satellite above the surface. So from here, so we need to subtract 1R. So the answer is R, which is option C. Then 1.8 is not the best. They're telling us that a warning siren in an ambulance has a frequency of this. And the frequency of sound is 330 in air. The ambulance is traveling at a constant speed of 25 meters per second towards the observer. This is the initial position, this is the observer, and then the ambulance passes. All right, so which graph illustrates the change in the frequency? So one thing we know from the Doppler effect is that when the ambulance approaches, the frequency is going to be high. Okay, the assumed frequency or the observed frequency is going to be higher. And then when the ambulance leaves, the frequency is going to start dropping. Okay, so which graph illustrates the change in the observed frequency? First one, telling us that the frequency is constant now, or it's decreasing. Okay. Then the second one just shows an increase in the frequency over time. Then part C, increase and decrease. Part D, decrease and increase. I'll go with C because it makes a lot of sense. Okay, frequency was high as the ambulance was approaching, and then it decreased. Then 1.9, which diagram below just describes the electric field pattern between 2-point charges of equal magnitude and opposite signs. Okay, so when you talk of opposite signs, which means there's going to be attraction. Okay, when they talk of equal magnitude, you normally look at the field lines. Okay, the number of lines leaving one sphere must be equal to the number of lines reaching the other. So this A is out since A is repulsion. B has some bit of sense, but when you look at it, the top part is a positive and then the bottom part is a negative. Okay, but when we look at the direction of the field lines, it's like they are moving from the negative towards the positive. So B is also out. When we look at C, positive, negative repulsion, that is out. Then D will make more sense. Then 1.10, they're telling us which of the following represents the correct use for electric field strength. So from our electrostatics, we know that the formula for electric field strength is given as this F over Q. We know that F is a force, which is newtons, divided by the coulombs, which is the same as Newton per coulomb. So B would make a little more sense. Okay, that is question number 1. Move on to question number 2. They're telling us that a log of mass M, okay, is pulled up the slope. Okay, we're saying a body remains at rest or continues in its continuous motion or constant velocity unless it's acted upon by an external force or a net force. Okay, we can just say that a body will continue in its state of rest, or we can call it motion at a constant velocity. Motion at a constant velocity. Okay. Unless acted upon by an external force. Unless acted upon by an external force. And call it external or even a net force. Okay. Then 2.2, they want us to draw a label diagram on the log. So when you look at our log, Since the log is moving upwards, so we say we're going to have tension there within the wire. There's going to be the FG parallel. But since the log is moving upwards, we can also have the frictional force down there. We're going to have the normal force and then the FG perpendicular, as well as the weight, same time. So 1, 2, 3, 4, we have around about 5 forces. So I can just draw something like this with a dot. I'll use my tension. I have my frictional force. Okay. This is going to be my normal force, Fn. Now I call it N, no problem. And then we can have our FG perpendicular, and then the weight will be acting downwards. Remember, we also have the FG parallel that is acting downwards. So that would be the free body diagram for 2.2. And then 2.3, they want us to calculate the mass of the log. The mass of the log. What do we know? Okay. So from the free body diagram, since we only focusing on the movement along the incline, we're just gonna look at the net force just within that sort of direction. So I'll say that my F net is equal to MA. Okay. Then I know that this thing is a net coefficient where moves up as well, but a constant velocity. Okay, there's something that is interesting also. Okay, so for as long as velocity is constant, which means the acceleration is going to be 0. That we need to know. Okay, so which means my acceleration is 0. So I'm going to have my tension force. Okay, since it's moving upwards, I'm going to subtract the sum of the FG parallel and the frictional force. This must give me the mass and the acceleration, which is a 0 now. Since A is 0. Okay. I have my tension, FG parallel, I can get it. My problem is the frictional force. Okay. So what I can do, remember, the frictional force is normally given as the mu K times the normal force, which is mu K times mg cos of the angle of inclination. So I'm going to use that. That is FG perpendicular, something like frictional force. Okay. So our tension minus, this is going to be mg sine theta, minus the mu K, the mg cos of theta must give us 0. Let's do the substitution. Remember, we said our tension was 1750 or 1570. Okay, 1570 minus the mass we don't know, but the acceleration is going to be 9,8. The sine of 12, I'll put m somewhere there. Then minus the mu, the coefficient was 0,3. Okay, that's going to be 0,3 m times 9,8. The cos of 12 is equal to 0. Then I can just simplify this part or those parts. So 1570 minus, and I punch that into my calculator. Since both of them are having m, so I can just ignore the m and just focus on the numbers. So that is 9,8 sine of 12. Okay, I'm adding the 0,3 times 9,8. Okay, cos of 12. That is giving me 4,9 something. Okay, 4,913 m is equal to 0. Okay. Then I'm going to move this that side. So 1570 is equal to 4,913 m times the mass. Then I'll divide both sides by 4,913. Divide by 4,913. So this cancels that. And then 1570 divided by 4,913. I'm getting 319,56. Okay. That is 319,56 kilograms. Okay, so guys, that is what we are having. That is what I am having. For question 2.3. Then 2.4. 2.4. They're telling us that the angle of the slope is now increased from 12 to 14. Identify the effect of the increased angle on each of the following. You only have to write increase, decrease, or remains the same. Okay, so when we look at the coefficient of kinetic friction, so when we look at the cos of 12 and the cos of 14, which one is bigger? Okay. From my calculator, the cos of 12 is 0.97, and then the cos of 14 is 0.97. Also, what's going on? Okay, the same cos of 12 is 0.978, and then the cos of 14 is just 0.97. So increasing the slope will kind of reduce the friction. Okay, so this will it affect the friction? No. This is the decreasing. Okay, but then how will it have on the coefficient? So coefficient will remain the same. Okay, that remains the same since it's a ratio. It remains the same, remains the same, remains the same. Okay, so 2.4.1 remains the same, and then frictional force is gonna decrease because of this decrease. But then they're telling us that the wire snaps, and then the log slides down the slope until it stops. Can we give a reason why this cannot be seen as a free fall or a projectile? Okay, so one thing we say about free fall is that motion must be under acceleration due to gravity entirely, okay? But in this case, as it slides down the slope, we have some other elements like friction. Okay, so it's not just gravity that is affecting it, okay? So the explanation is that we have external forces, okay? You can say the presence of external forces. External forces other than gravity, acceleration due to gravity. Example, we said friction is one of them. Okay. Then that is 2.5. Let's move on to question number 3. Question number 3, they're telling us a softball is thrown vertically downwards or down towards the ground, whether after it bounces back or where after it bounces back up as shown in the diagram. Okay, then they're telling us that when the ball reaches point A, it has a speed. Softball is thrown vertically down towards the ground. Okay, then the height at A is 5,0 meters above the ground, and then the ball hits the ground and bounces off to maximum height at position B. Okay, if we assume that air resistance is negligible, what is a projectile or what is projectile motion. Okay, so projectile motion is more like the same as before. Okay, so it's motion under the influence of only gravity. So someone can say moving object that is influenced by just gravity. Then 3.2, they want us to calculate the speed of the ball as it hits the ground. So we have the displacement, okay, which means our change in y or delta y is 5 meters. Our VI is 8.4 meters per second. Now they want us to get the VF. Which formula can we use? Can use the V squared. VF squared is equal to VI squared plus 2G delta Y. Okay. So we have G, it's only Y that, no, it's only VF that is shortened. Okay. So VF is going to be the square root of 8.4 squared plus 2. Since the object is moving downwards, I'll take it to the positive direction. That is 9.8 times 5. Okay. And I punch that into the calculator. Having 8.4 squared plus 2 times 9.8 multiplied by 5. Okay, I'm getting 12.983 meters per second. Okay, can I just confirm with the instruction whether it's 2 decimals, so I don't want to implement my own. Round off your answers to a minimum of 2. Okay. So it's going to be 12.98. They say the minimum smallest, so it's okay. Even 12.98 would make a lot of sense though. All right, then we move on to 3.3. Can we show by calculation that the time taken for the ball to reach the ground is 0.47? So now we've been given a question and we've also been given the answer. Just need to get 0.47. Okay, so time is what we need. Okay, now I don't know how people do this, so look at it. It's a 3-mark question. Remember, we have V final is equal to VI plus GT or AT, and then delta Y is equal to VI times T plus a half Q T squared or delta T squared. Okay. I don't know which one but we can try this. Okay, first formula if we are sure of our answer that we got in the previous question. If we have any doubts, then you go with the second approach since it doesn't have final velocity. Okay, so I'll try both of them and see if I get the same thing. VI plus G times delta T. So our VF was 12.983 is equal to the VI, which is 8.4 plus, that's going to be 9.8 times T. So the object is still dropping down. I'll move the 8.4 that side, so 12.983 minus 8.4. That's giving me 4.583 is equal to 9.8 T. Then divide both sides by 9.8. Okay, divide by 9.8. I'm getting 0.468 which means it's approximately 0.47 seconds. Okay, perfect. Let's try with the second approach and see. If you look at the change of the delta y, it's VI delta t plus a half g delta t squared. So this is more like a quadratic. So if that is a 5, that is 8,4t plus a half times 9,8 t squared. I can group everything to one side so I have a standard form. So that's going to be 4,9 t squared plus 8,4t minus 5 is equal to 0. Then I need to use my quadratic formula. That's b squared minus 4ac over 2a. So our b is 8,4 plus minus the square root of 8,4 squared minus 4 times 4,9 times negative 5. This is over 2 times 4,9. Guys, let me see if what I'm saying makes sense, okay? We are adding the square root of 8,4 squared minus 4 times 4,9 times negative 5 over 2 times 4,9. Okay, I'm using a plus sign. If I use a plus sign, which means it's 0.47 seconds. Okay, and then if I switch the plus sign to a minus, I get negative 2,818 something. So I get the same answer. All right. Then we're done with this. The ball bounces off vertically upwards with a speed of 4,2 meters as it leaves. Okay, and then the time that the ball is in contact with the ground is 0.2 seconds. Are asking us what is the magnitude and direction of the acceleration of the ball at the point B. Okay? So regardless of the point where the ball will be, the acceleration and its direction will always be the same. Okay. So in this case, whether it's at B or at A, the acceleration will always be 9.8. And which direction does acceleration work? It must be downwards. So 3.4.1 is going to be 9.8 meters per second squared, but downwards. All right, then 3.4.2, they want us to calculate the maximum height that the ball reaches after the first bounce. Okay, so they gave us the initial velocity. Okay, so I'm gonna take the 4.2 to be my initial velocity for this part of the journey. Okay, so that my VI is 4.2. Now that my VF is gonna be 0, but my G is going to be negative 9.8. Okay, so maximum height. I need to look for a formula that I can use. I use VF squared, where it makes sense, is 3.4.2. Okay, VF squared is equal to VI squared plus 2G delta Y. Okay. We know that the V final at B is going to be 0. Is equal to our VI. We said it's 4.2, but we say it's moving upwards, so I'll make it to be negative. And then plus this is 2, the G is going to be negative 9.8 times my delta Y. It was negative because the object is moving upwards. Then 4.2 squared is giving me 17.64. This is going to be minus 19.6y is equal to 0. So I can move that side, so that 19.6y is equal to 17.64. Divide both sides by 19.6. Okay. 19.6. I'm getting 0.9 meters. So the height at B is 0.9. Okay, then 3.4.3, they want us to sketch a velocity time graph of the motion of the motion from the moment that the ball passes A until it reaches point B. It's for 6 months. Okay. So one thing we need to know. Okay, remember it's a velocity time graph. So this will be velocity in meters per second. And then we can have the time in seconds here. So initially, the velocity was 8.4. Okay, when it hits did they give us any points of reference? No, they never told us. So it can be a two type of graph. So we could assume that if this is our 8.4, it's gonna increase up until we said 12.983, something like that. Okay, so we can connect line. That's up until it hits the ground. What was the time when it hits the ground? We said it was 0.847. Okay, but they told us that it takes 0.2 seconds for it to interact. Okay, so 0.47 plus 0.2, I'm getting 0.67. So from somewhere here, that is 0.67. Have this. Okay, the body had 4, something, negative 4.2 meters per second. Okay, and then it went on, and then it reached point B, where the velocity was 0. So that is our point B. When I need the time, I can find the time. Since they say the time taken for the ball to reach the ground and leave the ground, the velocity of the ball has reached the ground. So we have the velocity of at A, which is done. Velocity of the ball has hit the ground. We have it. The time taken for the ball to reach the ground, which is the 0.47, and then leaving the ground, we have that. The velocity at maximum height at the, so just that. We don't need the time there. So guys, that's how the 6 marks would be allocated. For as long as whatever you've been given is being represented, then we're good to go. So these will be just dotted lines because these are intervals between which the ball is bouncing. Okay, someone might even draw the connection line. Not a problem. 3.5. They're telling us that the soft ball is replaced with a very hard ball. How would this affect the following? Okay, increase, decrease, or remain the same. Okay, the contact time. So we know that a soft ball would take longer on the ground. Is that true? Will it take a shorter period of time or a longer period of time? I don't know. Guys, help me. Short or long? I'm not sure. I'm not sure. Okay. So softball, since it's soft, it will take long. That is true. And then the hard ball will take less time. So softball, is this, how will this affect the contact time? So the contact time is going to decrease. Okay, that is true for the fact. And then how about the time that the ball, or the height of the ball after it strikes the ground? Now, since the contact time decreased, okay, then what's going to happen to the height? The height is going to increase. Okay, since there's going to be more time for the ball to move upwards. Guys, that is question number 3. Question number 4. They're telling us that a ball X with a mass of 50 grams, and then there's another ball Y with a mass twice as X, are supported by long strings from a ceiling as shown in the diagram. So we say ball X with 50 grams. So this is going to be 100 grams. Since they said it is twice. All right. So the balls are each pulled back and released so that they move towards each other. And when the balls collide at the position as shown in the diagram, the strings are vertical. Then the balls rebound in the opposite directions. The velocity of X after the collision is 2,1. Okay. After the collision. So if this is X and this is Y, initially it was 4,5. Finally, it's a 2,1. For Y, initially, it's 2,8. Finally, I don't know. 4.1, state the principle of conservation of linear momentum. So one thing we know is that in an isolated system, momentum is conserved. Okay, momentum remains the same. So I can see that the total linear momentum in an isolated system, I can say that the total linear momentum remains the same. That means constant or is conserved, no problem. And then 4.2, they want us to calculate the velocity of the ball Y immediately after the collision. Okay, so they want the VF of the Y. All right, so we're gonna say we're gonna apply the conservation of momentum. That is 4.2. 4.2. Okay, so we say momentum before collision is equal to momentum after collision. That is according to the principle of conservation, okay? And we know that momentum is mass, okay, the mass of X times the VI of X plus the mass of Y times the VI of Y must give us the mass of X times the VF of X plus the mass of Y times the VF of Y. So now in this case, direction is going to play a very big role. When we look at X, if I take the direction of X to be positive, then the opposite direction has to be negative, okay? So then that's going to be the mass of X, which is 50. Did they say 50 grams? Yeah, ball X with a mass of 50 grams. That's correct, okay? So I'm going to say 50 times the V initial, which is 4,5, as we stated, plus the mass of that, which is 100, times the initial velocity, which is 2,8, but in the opposite direction, okay, is equal to the mass of X, which is 50. When we look at X after the collision, it bounces off. Remember, they told us that the velocity of X at the collision is this to the left. So it's going to be a negative 2,1. Okay, negative 2,1 plus the mass of Y, we said it's 100 times the velocity final, which must be positive. Okay, so on my left-hand side, I have 50 times 4,5. All right, so 50 times 4,5, what do I get? Come on, I'm getting 225. Okay, and then that, let me just put a minus ones, okay? Minus, that's 280 is equal to 50 times 2,1. That's gonna be 105. Yeah, 105 plus 100 BFY. I simplify that, 225 minus 280, that's negative 55. When I move this to that side, it's gonna be plus 105 is equal to 100 BFY. Minus 55 plus 105, I'm getting a 50. Is equal to 100 VFY. Then I'll divide both sides by 100. Over 100 and over 100. So which means the velocity final of y is going to be 0.5. Okay, this is meters per second, but the direction is to the right. Guys, that's how I would have determined my 4.2. Then 4.3 is the collision elastic or inelastic. Explain the answer by use of suitable calculations. Wow. Okay. So guys, what we said was for as long as the collision is elastic, okay? Number one, there has to be conservation of the kinetic energy and the momentum. So we're not going to focus much on the momentum because it's obvious in both it's conserved. Okay, so for inelastic, there's just momentum. And then there's no conservation of pk. Okay, so no conservation of pk. So let's see. I'm going to look for the ek before, and then I'm going to look for the ek after. So if the ek before is the same as the ek after, then it will be elastic. If the ek before is not the same as the ek after, then it's going to be inelastic. Okay, so that's going to be a half. Let me just break it down here a bit. So we're going to say the ek before of x plus the ek before of y. This is the ek before or ek after of x, and then the ek after of y. So that's a half the mass of x, the v initial of x squared. And then a half the mass of y, the v initial of y squared. Let me do the substitution. So that's going to be a half. The mass was 50, okay, times the initial velocity. We said it was 4,5. Okay, this is 4,5 squared. Plus the y brackets now. Okay, so that's a half. The mass was 100. And then the velocity initial, remember it's a negative 2,8. And then square that. So that is 50 times 4,5 squared. I'm getting 506,25 plus. That's a half times 100 times 2,8 squared. I'm getting 319. When I add up that, this is 506.25, getting 898,25. Okay, this is energy, so it's going to be in joules. Then I'll look at the ek after. Okay, that's a half mx v final of x squared plus a half of my V final of y squared. So I have the mass is still the same. The final velocity of x, they told us it is 2,1. Okay, so it's negative 2,1 squared. That's a half. The mass is 100. The velocity will go to 0,5 positive squared. Okay, so that is 50 minus 2,1 squared. I'm getting 110,25. And then that is, okay, times 0,5 squared. I'm getting 12,5. So 110.25 plus 12,5. I'm getting 122.75 joules. Now, since the EK after is not the same as the EK before, okay, so it's saying EK before is not the same as the EK after, then the collision is inelastic. Okay, the collision becomes inelastic. So guys, that would be my approach to this question. Okay, if there's a difference, please you help me out. Okay, did I do something wrong? Someone is saying, why are your masses in grams? Why are you keeping the masses in grams? Now I could divide them. I could divide the masses by 1,000. There's no problem. I divide this by 1,000 and then I'll get my 0,9 joules. Divide by 1,000, I'll get my 0,12 joules. But still, it seems that the EKs are not the same. All right, so that is 4.3. Then 4.4, they're telling us that ball X and Y are replaced by two identical balls. How would this affect the conservation of momentum of the system if the initial velocities remain the same? Remember, momentum on the system will always be conserved, okay? Will always remains constant. So this, we are saying, remains same. Okay. What is the reason? Okay. They're telling us that the initial, why am I saying initial? You can say that momentum before collision will be the same. Will be the same as the momentum after collision. Okay, that's for question 4. Then question 5, they're telling us that the mass, a ball of mass 0.03 kilograms moves along a curved track as shown in the diagram. So the height is 0.31 meters above the ground. And then we're being asked that the speed of the ball is v when it is at point A at that height, and then the ball moves down the frictionless track and collides with the vertical wall B. And the kinetic energy of the ball just before collision is this much. After the collision, the ball rebounds up the track. Ignore it. They want the principle of conservation of mechanical energy. Okay, so still you can say that in an isolated system, okay, the total mechanical energy remains the same. Remains the same, remains constant. If as long as there's no interference, we get the same mechanical energy. Remember, mechanical energy is a combination of EP and EK. Then they want us to get the velocity V of the ball at point A. Velocity V, what did they say? Okay, it's V, it's a point A, move on the track, blah, 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 blah. They're telling us the kinetic energy, okay, of the ball just before the collision with the wall is 0.12, just before. So remember, from this point, our height is going to be 0. Okay. We know that EP is mass, the force of gravity, and then the height. So at this point, where it starts rolling along the horizontal, there is 0 EP. The EP is 0. So what is there is the EK max, maximum kinetic energy at that point when it hits the wall. So I might use this 0.12. Let's see. Okay, so it means my energy at this is just 0.12 joules. And then at A, there's mechanical energy. There is some bit of EP, and then there's some bit of EK. Okay. So when I combine these two, they must be able to give me the 0.12 joules. So that's the assumption that I'm going to use at this point. Okay, so I'll say that EP, this is 5.2. Okay. Saying EP at A plus the EK at A must give us 0.12 joules. EP, we said mass, gravitational, and the height. This is a half mv squared, must give us the 0.12. What's our mass? We said it was 0.03, if I'm not mistaken. Okay. Then times 9.8 times the 0.31. This is going to be a half times 0.03 v squared. 0.12. I look at my left, 0.03 times 9.8 times 0.31. I'm getting a very small number. It's 0.0911. Then 0.03 divided by 2. I'm having 0.015. Squared is equal to 0.12. Then I'll move this to the left. So 0.12, I'm subtracting 0.0911. Okay, so 0.15 is squared. It's going to give me 0.06289. Okay, then now divide both sides by 0, what's wrong here? Everything. So that is 0.015. Okay, so 0.015 over 0.015. So that cancels that. Okay, before I find the square root, let me try to simplify this. That's going to be 1.92667. The square root of the answer is going to give me 1.38, 1.39 when I round it off. Okay, that is meters per second. Guys, that's how I've gone about that. 5.2. Then 5.3, they're telling us that the change in momentum of the ball due to the collision with the wall is 0.096 kilogram meters per second. Change in momentum, it's like the impulse. And the ball is in contact with the wall for a period of 0.02 seconds. So for hitting the wall, or for the ball hitting the wall, can you calculate the speed immediately after the collision? The speed immediately after the collision. Okay, what do we think we're gonna use? Anybody? Nobody. Okay, so one, they want the speed immediately after the collision. So we're gonna use, since they gave us the change in momentum, is M, that's V final minus V initial. Immediately after the collision, so which means they are looking for the VF. But we know the velocity with which it hit the wall. We don't know it. So I see two approaches to this. Okay. Since I have the mass, I might just get it directly. Like directly. That would make some little sense. Okay, no, it's fine. Let me get the velocity with which it hits the wall, which is my VI. Okay, so since at point B, it's just gonna have the maximum EK. Okay. So we're saying at B, let's do this. Let's move this. Say that at B, there is maximum EK, which is a half mv squared. That will be the same as our EK max. Okay, so that's a half times 0.03 v squared is equal to the 0.12 joules. Okay, so v squared is the same as 0.12 divided by 0.015, and I divide both sides just to be sure. Yeah, then I need to find the square root of that. 0.12 divided by my answer, I'm getting 8, and then square root of my answer, the square root of 8, ending up with 2.828. Let me check the whole of it the way it is, so that I can get a more correct answer at the end. Okay, then we're saying change in change in momentum is m v final minus v initial. Okay, when I do my substitution, we say that our change in P is 0.096. The mass is 0.03. V final, we don't know. This is 2.828. And divide both sides by 0.03. Okay, 0.096 divided by 0.03. That's going to give me 3.2. Okay, is equal to VF minus 2.828. Then I need to move this that side, so that will be a plus. Okay, so 3.2 plus 2.828. 828. That's giving me 6.0. 6.0 8. So I can round this off to 6,03 meters per second. Makes sense though. Something's off. Did I mess up somewhere? Wait, I did. Something's off. Okay, changing momentum of the ball with the collision. I think it's my directions that I need to play with. So it's going to be negative. That is negative 3,2 plus 2,828. Since I'm assuming that the coming down of the incline is positive, but now it's moving off. Okay. I'll do it the other way around where I plus that, and then that is a minus. Okay, so negative 3,2 plus 2,828. I'm getting 0,3 something. 72. Okay, so it's going to be 0,372 meters per second. But in which direction? In the opposite direction. Yeah, this makes more sense. I don't have 2, then I have a 6. Okay, then question number 6. Diagram below shows a fair ground carriage that is moving at a constant speed of 9,8 to the frictionless surface. Total mass of the people and the carriage is 600 kilograms. Carriage moves at a slope that is 30 degrees to the horizontal, and it comes to a stop after traveling the rough surface of 4,1 meters at point C. Oh, vertical height, okay. Then they state the work energy theorem in words. Guys, thank you for my skipped question. 5.3.2, they want the magnitude of the average force on the wall. Okay, so sorry guys. 5.3.2. Okay, we know that F net times delta T must give us delta P, change in momentum. Okay, in this case, the question is asking for the magnitude of the average force. So since we already have our change in momentum, which is 0,096, this is F net multiplied by the time, which they told us was 0,02 seconds. And I'll divide both sides. So 0,096 divided by 0,02. All right, punch that in the calculator, I'm getting 4,8. It's a force, therefore we have 4,8 newtons. All right, then I can happily move on to question 6. There is a constant speed of moves at a constant speed. Remember, constant speed represents zero acceleration. They want us to state the work energy here in words. Now, we said that the net work done is equal to the change in kinetic energy. Just as simple as that, okay? You can say that the net work, someone I think talking of product of cells, it's the net work done on an object, okay, is equal to the change, okay, the change in kinetic energy. just that. Then 6.2, can we calculate the kinetic energy of the carriage and passengers as they reach point B? The kinetic energy. Will this be hard? So EK at B is a half the mass and the velocity squared. So that's a half the mass was 600 according to the information. Okay. The velocity is 9.5 squared. So 600 times 9.5 squared, I'm getting a very big number. That is fine. It's 27075. All right, then 6.3, can you draw a free label diagram of all the forces that act on the carriage as it moves up? Okay, so we know that the incline is rough. So there's gonna be force applied, or the force that is pulling this carriage up. Okay, then there's going to be the FG parallel, that is a must as long as there's an incline. And then there's gonna be frictional force. You can have the FG perpendicular, you can have the normal force, and then you're gonna have our weight somewhere there. What is the question asking for? The carriage, constant speed, then it comes to rest. Okay, so since there's nothing pulling this, and it's like it came with some bit of velocity just to climb and come to a stop, then there's not gonna be any force applied there. Nothing's pulling it up. It's just taking itself up. I think I'll have this. Let me just pour it out nicely. It's saying this is 6.3. That's yes. Okay, so say this is gonna be normal force. People call it N. I might call it Fn. This is Fg perpendicular. It's going to be Fg parallel. Okay. So there's also gonna be frictional force that is acting downwards. And then we can have even weight. Okay, so guys, that's all the forces that will be acting on that board. Okay, then use the energy principles and calculate the frictional force between B and C. You want us to get the frictional force between B and C. Okay, so now since we were talking about the change in kinetic energy, I think that's what we're gonna use. So you can say that the network, okay, between B and C is equal to change in kinetic energy, which means the kinetic and the EP. I'll get lost when I put that. Let me just use the EK, change in EK, and then change in EP. Say EK, why is it KE? All right, so I'll say that my Fnet or Wnet is the same as the change in kinetic, my final kinetic, since this thing is coming to a stop, which means the velocity is going to be 0 at C. So it's going to be 0 minus the initial that we got, okay, which was 27075, plus the change in EP, Okay. So at the bottom, at this point P, you know that EP is 0 and EK is maximum. At this point, the EK is 0, and then the EP is at its maximum. Okay, so that's going to be my final, which is the MGH. Okay, let's start like that. This is MGH minus something like that. Okay, so I'm getting my 600 times 9,8 times our height, which is 4,1. Okay, and then subtract the 0. Not going to have any effect. Okay, that's negative 27075 plus this is 600 times 9,8 times 4,1. That's giving me 24,108 joules. When I combine it with 27075, I'm getting a negative answer, which is fine. Okay, that's negative 2,967 joules. Okay, so that is the network done. Okay. Then I'm going to look at now the aspect of the individual forces that are working on this carriage. Okay, so which means the FG parallel has to do some bit of work. The friction has to do some amount of work. Okay, so how am I going to represent? How am I representing that? So I'll say that we know that work done is force times delta X and the cos of theta. Okay, just from here, WF. Then I'll have my F times my delta X, the distance here. How do I find this? Now, since I have this opposite side, I have the angle. From my trig ratios, A, opposite, and hypotenuse, I think I'll use sine. So which means I know that sine of 30 is 4,1 over the BC. And then BC is going to be 4,1 over sine of 30. So this is what I'm going to use for the displacement. Okay, so I'll say my displacement is 4,1 over the sine of 30 multiplied by the cos of 180. The reason being, it's moving in the opposite direction, this frictional force. This must be equal to negative 2,967. Then when I simplify my left-hand side, 41 over sine 30, I'm multiplying it by cos that. And that's 82, negative 82. F is equal to negative 2,967. Then I'll divide both sides by negative 82. Okay, 2,967 divided by 82. I'm getting a 36,182. Something wrong. Did I use 41 or 4,1? Oops, sorry guys. So 4,1 divided by the sine of 30. This is 8,2. Okay. If it's 8,2, then it's going to be 2967 divided by 8,2. That's going to give us 361. 829 or 83. It's a force, so it's will be Newton. All right. Then 6.5. They're telling us that a small tractor that is rated 9 kilowatts and pulls an empty carriage across the ground at a constant speed with a horizontal force of 300 newtons. Can we define what a non-conservative force is? Okay, so we know that a non-conservative force is a force in which the work done will depend on the path that is taken. Okay? So it's saying it's a force with which the work done is dependent on the path that is taken. And then 6.5.2, they want us to calculate the time that it will take for the tractor to plow an empty carriage for a distance of 850 meters. Okay, so we know that work done, remember we said F times delta X, the displacement, and then cos of the angle. Okay. So we can use this for work done because initially we know that power is work, the rate of doing work. So we have our power, we want the time. We can find this work done. So I'll start by saying power is equal to work done over time. But work done is force, displacement, and the cos theta. So what's our force? We told us there's a horizontal force of 300. Okay? So that's going to be 300. They told us the displacement is 850. Okay, so times 850. And then times the cos, I'm going to use 0 since it's not acting in the opposite direction. So 300 times 850 cos of 0, I'm getting 255,000. This is chosen. Okay. Then I'll do my substitution. We know that the power that they gave us was 9 kilowatts. Okay. So 9 kilowatts is the same as 9 times 1,000, which is 9,000 watts. So I'll say 9,000 watts is equal to 255. 255,000 divided by the time. And cross multiply so that I have my 9,000 T is equal to 255,000. Divide both sides by 9,000 over 9,000. Okay, so this is giving me 28,33. Okay, that would be seconds. So guys, that's how we get that 28,33 seconds. Then 6.5.3, how would the time change if a tractor with a greater power output was used? Remember, power is work done over the time. So we can see, okay, that power is indirectly proportional to the time. If the power is more, which means the time taken is going to be smaller. And then if the power is less, then there's a lot of time that's going to be wasted. So how would the time change if the tractor with great power? Okay. So if the power increases, okay, the time definitely has to decrease. I'm gonna say decrease. And then what is the reason? We're saying that power is inversely proportional. Is inversely proportional to the time. Okay, so you can say that as power increases, the time must decrease. Time decreases. Because in all scenarios, we're going to take the work done to be constant. Okay, if work done is constant. Then question number 7. Question number 7. We're telling us two charge spheres, A and B, are placed 15 centimeters apart in a vacuum. Sphere A has a charge of positive 3 PC. Okay, and sphere B has some unknown positive charge. The arrangement is illustrated within the diagram below. All right, then they tell us that point P lies on the same line joining the spheres with a distance of 5 centimeters from A. Can we define what electric field is? Electric field. So since it's a field, we can say it's a region of space. Okay, it's a region or space in which an electric charge will experience a force. Experiences a force, a region of space where an electric charge will experience a force. Then 7.2, they want us to get the net electric field strength at P. Okay. No, they're telling us the net electric field strength at P is 0. Okay, so E net is 0 at P. Can we calculate the charge on sphere B? So which means we're gonna look at the electric field at P as a result of A, and then at P as a result of B. And then we get the net that they want. Since both of them are positive, so there's going to be some bit of recursion. Okay, let's see. So 7.2, we're saying 7.2. So we know that A is going to be KQ over R squared. And then the E of B, the electric field at B, is going to be KQ over R squared. Okay. So that's going to be, remember this P, we said micro is times 10 to the negative 6. N is times 10 to the negative 9. Okay, and then pico is times 10 to the negative 12. All right, so I'm going to say 9 times 10 to the 9 times 3 times 10 to the negative 12 over our distance is 5 centimeters converted to meters. I'm going to say 5 times 10 to the negative 2. I can divide the 5 by 100, which is going to be 0.05 square root. Okay. If that happens, what do I get? Okay, let me punch that into the calculator. I'm saying times 3 times 10 to the negative 12 over 0.05 that squared. I'm getting 10.8. Okay. Then I come this side, look at the B1. It's going to be 9 times 10 to the 9 times the Q over the distance. Now, since this is 15, which means this total distance is going to be 10 centimeters. Okay, 10 times 10 to the negative, say 2. And then you square that. Okay, so it's going to be 9 times 10 to the exponent of 9 over, I'm having 10 times 10 to the negative 2, but then I'm squaring that. So I'm getting quite a big number, which is 9 times 10 to the 11, but with Q. So if that is true, then I need to apply my net formula. Is that true? Something's wrong. Apply the net formula. Okay, where we are saying E net will be the same as the EA plus the EB. Okay, now since it's a 0, which means that it is going to be a subtraction there. So say 0 is equal to my EA, which is the 10,8 plus this negative 9 times 10 to the 11 cubed. I'll move it that side, which is going to be 9 times 10 to the 11 cubed is equal to 10,8. Then I'll divide both sides by 9 times 10 to the 11. 9 times 10 to the 11. Okay. And then my Q, then divide by that, you're getting something big. Getting 1,1. Divide by 9. How do you get to 1,8? Divide by 9 times 10 to the exponent of 11. Getting 12, 12 times 10 to the negative 12, which is 1,2 times 10 to the negative 13. Someone can state it as 12 PC. Remember, it is a positive. All right, then now we have the charge. Okay, then they want us to state Coulomb's law. Okay, Coulomb's law simply tells us that the magnitude, okay, just get to the side, this is 7.3. So the magnitude of the electrostatic force, okay, between any 2-point charges, between any 2-point charges, okay, is directly proportional. Is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of their distances, distance apart. But some people will say the square of distance between the centers. So then done with that. 7.4. Charge B is replaced by negative charge of this magnitude. Now, calculate the magnitude of the force between A and B. Now remember, A is having a 3 PC. Now this is a negative 12 PC. They want the force. So we said force is the same as K, Q1, Q2 over R squared, or I can say QA and QB. Now substitute that. 9 times 10 to the 9. Something's not up. Let's see. Okay, then times, why am I saying 10? Saying 3 times 10 to the negative 12. Multiplying by 12 times 10 to the negative 12. The distance is still the same. So it's 15, which means it's going to be 0.15 squared. You can do that. And then put this in the calculator. 9 times 10 to the 9 times 3 times 10 to the negative 12 times 12 times 10 to the negative 12 over 0.15, that's squared. I'm getting 1.44. My pen behaves. Okay, it's 1.44 times 10 to the 11. I don't know if that would make sense, but it's a force, so it's going to be in newtons. Because I'm having 14.4 times 10 to the negative 12, which means when I simplify it further, I should be able to end up with that. I don't know, guys, what you're having, but that's what I get. Then we look at 7.5. Someone will say, now which direction is it? Doesn't matter. Remember, it's a positive and negative, so it's going to be attraction. So how would the magnitude of the force calculated in 7.4 be affected if the distance between the charges is decreased? Okay, so guys, remember, this is KQA QB over R squared. Now, regardless of whether the R is squared or it's just a plain R, we're seeing that F is inversely proportional to R squared, which means when you decrease R, or the distance between, the F must increase. And when you increase the F, the force must become weak or small. So the answer to this is going to be increase. Okay, now they need an explanation. We can just say that the force is inversely proportional. Okay, the force is inversely proportional to the distance, or the square distance. The square distance of separation, or the distance between the charges. I don't know, I feel like that would be enough. That would be enough. Now we're doing this with just a condition that if the charges remain constant, in other words, the magnitude of the charges remain constant. Guys, that is question number 7. Question number 8. An experiment is conducted to investigate the relationship between the force experienced by a charge if the electric field strength is kept constant. Okay, so we have the force and then the charge. There we go. Then they even drew for us a graph, okay, which graph is kind of a straight line from 0, and it's an increasing graph. Then 8.1, they're asking us to define what an electric field at a point is. Okay, so this is just a force that is experienced per unit positive charge placed at that point. Placed at that point. The force experienced by unit positive charge. Then 8.2, can we give the relationship between force and charge? The relationship between force and charge. So since the force and the charge are showing an increasing straight line, then we can say that force is directly proportional to charge, because as charge increases, even the force will increase. So you can say that force is proportional directly proportional to charge. An explanation is that increase in charge, okay, leads to an increase in the force. Let's say an increase in the charge. It's to an increase in the force, because we know that charge is independent, and it's the force that depends on the charge. Okay, use the information above to calculate the gradient of the graph. So gradient, remember, from our mathematical approach, you can get any values. I think I can use this point since it's on the line. I'll get my triangle. I'll get my change in y. And then this would be my change in x. Okay, so which means my gradient is going to be 0,2. Okay, 0,2. I'm dividing it by 30 times 10 to the negative 9. It's going to be 30 times 10 to the negative 9, since it's in nanocoulombs. I don't know, guys, whichever values we can get, I think it would make a lot of sense. Okay, so with what I have 30 times 10 to the negative 9. It's a very big answer, but it's fine. Having 6,67 times 10 to the 6. Remember, it's a force and charge, so it's going to be Newton per coulomb. I don't know, that's what I'm getting. So it all depends on which values you're going to use. Okay, these look like estimates. So anything that you use would make a lot of sense. Then they want us to get the value of x. So value of x, at x, we know that the charge is 63,8. This is going to be 8, but why can't I write it somewhere? 8,3. Okay, so since this is a straight line that is passing through the origin, the equation is going to be 6,67x. Why am I doing that? Why am I doing that? Let me avoid using this language of x and y. Let me say the force It's gonna be 6,67 times 10 plus 6 times the charge. Okay. Now our charge is 63,8. So that's gonna be 6,67 times 10 to the 6 multiplied by 63,8. I'm getting 425. I don't know if that would make sense. Let's say 425 and something. It can make sense. But if we look at it, because remember it's force over the charge, okay, force over Q, which is like the electric field. Okay, so if this electric field is 6,67 times 10 to the 6, but still, so I meant to multiply this by -9. Yeah. So 3 times 10 to the -9, which is going to give me 0.025, which is approximately 0.3. It's fine, 0.3 times. So same thing, whether I use this or you use the equation, end up with the same thing. Then 8.4, they want us to draw electric field pattern around the charge if it had been a negative charge. Okay, so one thing we know about an electric charge is that field lines must be seen entering. So we'll have that. And remember, the field lines must be perpendicular. Oops. Is that really a field line? Are you sure? Let me just make it something like that. So the arrows must be seen to be entering, regardless of how many they are. I don't know, that would make a lot of sense. Then question number 9, it's the last one. Hallelujah. Okay, so one way to tell if a mosquito is about to bite is to listen to the Doppler effect of the sound emitted by the mosquito as it's flying, okay? So which means as the buzzing sound increases, which means the mosquito is closer to you. All right, so the buzzing sounds, or the buzzing of the mosquito's wings, emits sound at a frequency of this much. And then the speed of sound in air is 330 meters per second. Can you state Doppler effect in words? Remember, Doppler effect is the apparent change, or is the change itself, okay? Relative to the motion of the observer, the listener, and blah, blah, blah. Okay, we can say that the change in the observed frequency, okay, sound detected by listener, or an observer due to the relative motion, between the source and the observer. Okay, so that change, either the listener is just stationary or is moving or whatever the condition might be. Okay, so they're telling us that if you hear a frequency of 1034 hertz, remember the mosquito emits a frequency of 1050. Okay, so if you're hearing 1034, does this mean that the mosquito is coming in for landing, or it has just bitten you and it's flying away? So since the observed frequency is smaller than what is being emitted, which means the mosquito is flying away. Okay, so we're gonna say this is flying away, like a flying fish, flying away, and then the reason is gonna be there's a decrease, or we can say the observed frequency is less than observed frequency is less than the actual frequency. Someone can say lower than, whatever the English people, English words that can describe that nicely. Calculate the speed of the mosquito when you hear the frequency of 1034. Calculate the speed of the frequency. Now it's moving away. So from Doppler formula, we know that the frequency of the listener is equal to V plus minus that, V plus minus Vs times that. Okay, so we have our V as 330. Okay, so that is 330. They want us to get the frequency. What's the condition? If you hear that this is moving away, the speed of this when you hear. We're not telling us where the person is seated. So they want us to get the velocity of the source. Okay, what we know is the frequency of the listener is 1034. The frequency of the source is 1050. Okay, so are we going to assume that the listener is just seated, doing nothing? Okay, if that is true, then we're gonna have frequency of the listener 1034 is equal to 330 plus a 0. Is it plus or minus? It's minus a 0. Over a 330, I'm gonna say plus. Why are we plusing? Because we want to increase the velocity down here so that the frequency is smaller. Then I'm gonna multiply this by 1050. Okay, step number 1, I'll multiply both sides by 1050. Okay, so 1034 over 1050 is equal to 330 over 330 plus Vs. We can do the cross multiplication at this level, no problem. So this, that. So I can put this in brackets, no problem. So 1034 times 330, that's going to give us 314,220. That's 1034 Vs is equal to 330 times 1050. That's giving me 346500. Okay, then I'm gonna move this to the right. So 1034 Vs is equal to this minus 341,220. Having 528 and 00. Okay, then I'll divide both sides by 1034 over 1034. Okay, so that becomes 5,106, which is like 11. meters per second. Guys, that's what I'm getting. Okay, then 9.2. 9.2. You're telling us the Doppler effect has quite a lot of uses. One of the uses in the field of astronomy while studying the stars is what we call a redshift emission. It's observed. When you have a redshift, is the star moving away from the Earth or towards? So in most cases, when you have a redshift, it's moving away. What is the reason? Because when you look at the red, just the color red itself, what would be the frequency of red? The frequency is the shortest. Okay, red has the shortest frequency. And we know that frequency is inversely proportional to what we call the wavelength. Okay, so which means if it is at a red shift, the frequency is small and the wavelength is big. So when the wavelength is big, it simply means that the star is moving away. If it moves to a blue shift, then the frequency is high and the wavelength is going to be short, which means it's moving towards. 9.2.2, they're telling us another use of Doppler is in the medical field. Can you give 2 uses of Doppler flow meter in humans? So one, it can be used to measure the flow of blood. Used to measure the rate of flow. Rate of flow of blood, rate of blood flow, no problem. And then it can also be used to monitor the heartbeat of the fetus. Monitor what we call the heartbeat. Is the heartbeat of the fetus. Okay, and you can also use it in what we call the ultrasound test. Estimate the blood flow within the blood vessels, or if there's any sort of blockage of any sort, we can still use the Doppler flow. Okay, guys, that's the end. Just gonna stop there. It was a long paper, but yeah, I hope we did our best. No? If there are any corrections, any positive and constructive suggestions, please you can